Okay, so today we're talking about experiment 4, fats, soaps, and detergents. So we're going to talk about how we make, what are soaps. You know, soaps have become even more important nowadays, given our global health crisis. But it's important to know what makes soap so important, where it comes from, and how these detergents and soaps are made, and how do we balance their helpful health effects for cleaning and antibacterial versus how hazardous are they to the environment. So it's important that we kind of go through the process of how we make these. Okay, so the experiment is pretty short, so it shouldn't take us a try. So learn about relative solubility of soap, fats, fatty acids, and what soaps are made of. Properties of amphiphilic, so that means like they both love water, and there's parts that don't like water, so they shy away, like oil does. We're going to talk about the mechanism of action of a soap. So you've probably gone over this in lecture already. And the mechanism for forming soap is nucleophilic acyl substitution. Then throughout the presentation, I'll talk about, we'll know about some green chemistry, and soap comes from natural resources. We can create it from vegetable oil, which we can obtain from plants and our natural world. Okay. So how does soap work? So you might have been introduced to the concept of a micelle, which is right here. So pay attention to this page, because one of the questions in the post lab, they want you to draw a micelle. So you draw something like this, you'll get full credit. So that you stay here, because I might board out something that might help you on the lab report. But if those of you who are doing very well, maybe you don't need it. Okay, so how does soap work? So well, soap molecules, they're composed of both a polar head and a hydrophobic tail. So the tail is going to sequester the, when you have dirty dishes, the soap, it forms suds, so it breaks up the water's surface tension. And what that does is it causes it to encapsulate or sequester the oil molecules. So it allows the soap to kind of interact with both the water and the organic compound, fats, oils that you're trying to clean off, like say your dishes or like laundry. So what it does is that the polar head groups will orient itself towards the water molecules, and the hydrophobic tail parts, non-polar parts, will associate with the oil. So I drew two representations here. See, the water is going to kind of form a boundary along. This is what we call micelle. So it's a 3D structure. So it's like an aggregate of these soap molecules that bundle up together to form this phenomenon. So micelles are also called, something forms micelles are also called surfactants, because they affect the water tension, the surface tension of the water, and that's what allows suds to form, and that's how you'll be able to be both soluble in water and at the same time targeting the oil molecules or whatever you're trying to clean. So here's another representation. Here, a little cartoon drawing. In the center will be your organic material, and on the outside is your water, where the water and the polar heads are. So interestingly, they use micelles can be used for chemical reactions too. If you have, like, say, a Grignard reagent, you can use a micelle to kind of encapsulate and do a Grignard reaction. So there have been reports where you can actually use these kind of things to do actual synthetic chemistry. Okay. So detergent. So what's the difference between soap and detergent? So soaps have a carboxylate as the polar head group. So right here, for example, calcium stearate. While detergents tend to be have sulfate, so a sulfate group here, or alkyl sulfonate or benzene sulfonate, which is right here, benzene sulfonate right here. So it's either a sulfate or a sulfonate, and the difference is sulfonates are better at dissolving in hard water, and that's because it has to do with a few things. So they're more soluble in hard water. So you're in Davis. When I was in Davis, the water was terrible. Like when you wash dishes, there's all this crud residue, and that's from the hard water because there's calcium in it, magnesium ions, maybe iron, maybe I don't know, zinc, who knows. But usually, you know, after you take a bath, shower, do dishes, there's some residue left over, and that's because the water is not really pure. It's hard with these ions. So detergents do not precipitate in hard water because their pKa doesn't allow this conjugate base here to be very strong. So it has really no affinity for these metal ions. So the base strength relates to, you know, the ability to coordinate to the ion and form a precipitate. So the pKa of like a benzene sulfonate or sulfate, you know, like -2, I think sulfuric acid is about -10, but sulfonates are usually -2, 0 to -2. Don't quote me on that. And carboxylic acids are about pKa of about +5. So there's a really big difference in pKa. So the higher pKa, meaning the higher base strength. So this is a better conjugate base. So it can actually coordinate to calcium and magnesium, and that's how. So you wouldn't use like hand soap to wash your dishes or your laundry, because if those ions got in here, like calcium, it would precipitate on your clothes and it'll make it even more dirtier. So that's why the detergents are usually in the form of benzene sulfonates or sulfates, because they have better properties even in hard water. So we don't know if our water source is hard or not. Hard just means it has like some concentration of minerals, so calcium, magnesium, and what it's set and so forth. So these tend to form precipitates. So take a look at these statements here. It will help you in part of the post lab, because they'll ask you about like, oh, what happened when we reacted our soap with ferric chloride, with calcium chloride? What happened? You know, you should have seen maybe a cloudy solution or precipitate forming. So this will be important. So come back to this if you need some help on that part of the post lab. Okay, so those are our soap and detergent. It's just the the polar group is just different for each class. Okay. So let's talk about the mechanisms. Here is my sample of triglyceride. So how we make soap is we take a fat and we hydrolyze it with sodium hydroxide or some alkaline base. So in this case, I'm going to abbreviate all my R groups so I don't have to write it each time. It's way too big. So what I do is it's the nucleophilic acyl substitution. So this should be familiar. So these reactions are fast. Like esters reacting with like strong base, depending on the concentrations, it's really fast. So it'll immediately form this intermediate, and then through equilibrium, it'll kick off this part of the fat. So eventually you'll get the intermediate, and what the driving force for this reaction is heat, right? So there's equilibrium. So the driving force is the favorable acid base, right? So alcohols are weak than carboxylic acids. So this reaction will happen very fast. So this will be pushed all the way to the right. So I'm going to go to this side of the products. So once I pull that equilibrium to this part, it'll pull the other equilibrium reactions that were previous, and that will cause my reaction to go forward in the forward direction. So we use a favorable fast step to isolate the products, and that's how we control the thermodynamics of the reaction and get like an unfavorable leaving group to leave, is because one of these steps is more favorable to forming the product. So we're going to do that again on both of these on both of the other ester groups here, 1, 2, and eventually we end up with glycerol, very water soluble, and we get our soap right here, 3 times 3 times of these chains. So that's 3 soap molecules. So in this experiment, you'll be making a soap and you'll be testing it. Okay. All right, so let's quickly go through the setup. You'll see this on activity, but it's also helpful to think about what's happening. Okay, so we're going to get cooking fat. So I think canola oil. In previous labs, we use Crisco, but same thing. It's just a canola. So what's the difference between oil and lard? Okay, so I think you talked about this in lecture. Oils usually have, they're usually unsaturated, so they have alkenes in their chemical formula. And then lard is like pure fat, so it's solid. So it's it's kind of gross. It's saturated, so it has all single bonds. So when it's saturated, it has a better packing in the solid phase, because if you have alkenes, there's going to be like kinks in the structure depending on if you're cis or trans alkenes. So this actually plays a role in like cis and trans fats. So when you have, usually these are oils or liquids because they can't pack well due to the double bonds in the structure. Whereas when you have all single bonds, it packs better in the solid state or the crystal state. And that's why fats, saturated fats, are usually solid and they have higher melting points. Okay, so we're going to add solvent. All right, what solvent do we use? Does anyone have an idea? What solvent? So we're going to mix fat, so it can't be water, right? We need organic solvent. So we're going to use ethanol, and then we're going to use a base. All right, so our base is going to be, we need either sodium hydroxide or potassium hydroxide. Those are the two things we usually use. And you ever see like those like oven cleaners, they're usually a solution of sodium hydroxide, or I think potassium hydroxide. And that's why when you get like oil or like fat residue in your ovens, you spray that remover, and you can wipe it up with water and a sponge. So it's essentially doing the same thing here. We're breaking up the fat and making it a soap. So we're going to add a base. So what is the concentration? So what we have is 10 mils, which contains 5 grams of sodium hydroxide. So from this information, we can actually calculate the concentration. So we calculate the moles, 5 grams divided by 40 for the molar mass, get 0.125 mole. Now, the concentration is 0.125 mole over 10 mils, convert that to liters, and we get 12.5 molar. So this is a very strong concentration, it's very high. So this reaction will go really fast. So that was just the background of calculating concentration. I don't think you need it for a lab report, but in case you do, it's right here for you. So make sure you can understand why I did these calculations, okay? So always ask questions if you have any. Okay. All right, so reflux. So what do we need for glassware? So let's remember when we did reflux last time, we used round bottom flask, condenser, heating manual, and stir plate. So I'm not going to show the diagram because we've already seen it before, but it's basically the same thing. We're doing reflux again. So I didn't mention last time, but it's important to grease the joints in this experiment, and that's because sodium hydroxide can actually splash on the joints, so like where the connections are made. And if you get salt, if it dries up there, it can potentially make the joint stuck, and the apparatus can no longer be taken apart. So that's a common error in these types of labs. When you heat things get hot, they can melt the joints together. So it's important that you use silicone grease so you can actually take it apart after you're done, because you don't want to break it. Sometimes there's tricks to solve this issue, but sometimes you just have to break things, and that doesn't make the boss happy. So just make sure you don't make that mistake if you ever work in a chem lab. Okay, so the reaction, it's 30 minutes. So here's a good question: do we start 30 minutes from when we turn on the heat, or do we start when it starts refluxing? All right, so think about that for a bit. I'm going to come back to it in a minute, or right now, actually. So you know, when you don't start from reflux, you're actually wasting time. So that time it takes time to heat up the reflux. So until then, you're probably not going to have enough energy to do the reaction. So it's not going to go very fast. So if you start from the time you turn on the heat, you may get lower yield because you need the 30 minutes of reflux time is important to drive the reaction forward. So what can happen if we start from 30 minutes? Well, our yield could go down, and that would not be good because we wasted time, wasted material, and now we have to go back and do it. All right, so we always want to stick to our directions and just think logically, what should we do? Okay, so after your reflux, you're going to remove the heat, let it cool. Then we're going to collect our soap. Okay, so we need to make a hot sodium chloride solution, and that's because we need a saturated solution to precipitate the soap. So why hot? Is so we can dissolve the sodium chloride, because dissolving 25 grams of sodium chloride in like 75 milliliters of water, that's not enough to dissolve all of it. So we need heat to help us do that. So we're going to pour the reaction into the hot sodium chloride solution. And the reason we do that, it helps precipitate the soap as a solid due to the ionic solution. So that basically means that there's a high ionic strength. So there's a high concentration of ions in the solution. So water will tend to only dissolve the more soluble component. So since salts are very soluble, and your soap is technically a salt, but it has some hydrocarbon chain in it, so it'll make it less soluble than a pure salt with just inorganic ions. So in this case, we want to make it saturated so we don't dissolve our soap, and our soap precipitates out. So that's called salting out, precipitate. So that's another way to isolate things or kind of remove your soap from your solution. It's taking advantage of water solubility. Okay, I had to do this a lot, and when I was in the lab, because I didn't want to evaporate water. It's very hard to do, and it's not very easy. So this method was particularly useful in certain physical transformations. Okay, so we're going to set up suction filtration like we've done all quarter. So we're dealing with a large amount of soap, so we want to use the Buchner funnel. Don't use the Hirsch funnel, that's too small. So we want to use the Buchner funnel, and we're going to use glass wool to filter. We don't use filter paper because if we use filter paper, the base solution will soak it up, and it will clog the funnel. So we don't want to do that. So we're going to use the glass wool, and glass wool is okay because we want the solid. We don't want to filter it. So the glass wool will prevent, the clogging of the funnel. So that's why we use glass wool to filter instead of filter paper. Okay, so we're going to only use enough to cover the funnel's bores. So we don't want to use too much because that might cause problems with filtering or draining the solution. So we don't want to do that. So it's only like a thin layer, like what a piece of filter paper would do in other situations. So we're just substituting those two things out. Okay. So what are we washing with? So we're going to wash. So since this is a soap, and the products, so let's just go over this. So how much? So we're going to use water, cold water. We don't want to use hot water because we might dissolve the soap. So use ice cold water. And you want to use a little bit of it because if you use too much, it can also dissolve the soap. So we don't want to do that. So what is removed? So if you think about the products of our reaction is glycerol, right? And we have ethanol in there. So ethanol will dissolve in water. So we can take that out, excess sodium hydroxide, and glycerol. Glycerol is very soluble in water. It has 3 hydroxyl groups on it. So we can remove it essentially from our soap using water because it'll prefer to associate with the water because it's very soluble and it has lots of hydrogen bonding. Okay. Where is the soap? Okay. So everyone, we know the soap. It's our solid we collected, right? So that's where the soap is. Okay. All right. So lastly, we're going to test the soap. And then we'll get to cleanup. So our soap solution, we're going to take just a tiny bit of our soap because we don't need too much. So to use a small amount, 0.1 mg. So for reference, that's just like the tip of a spatula. So you just eyeball it here. Then we make the detergent solution. So we're going to use like a few drops of detergent. And then we're going to test with plain water as control. So when we use both of these, they should dissolve pretty much in the same manner, because soaps, detergents, they're both polar, so they should dissolve in water. Okay. Then we're going to test with oil. So remember, oil, as I said on my other slide, oil shouldn't be a problem. Only that becomes a problem is when we do like ions. So in this case, water, oil, both of them should form suds. Okay, now we test with calcium chloride. Remember, calcium is not very good with soap, but so a precipitate should form because we get calcium, for reference state, stearate, but it could be anything. It could, depending on what the structure of your fat is. But detergent won't produce a precipitate member because of its because of the sulfate groups. They're not as basic as carboxylate groups, so they will not interact with calcium. So they'll produce suds as usual. Next, we're going to test with ferric chloride. Soap should precipitate again because remember, iron is one of those minerals that are kind of hard. The reason why we don't precipitate sodium and lithium is because they're readily soluble, so they don't tend to precipitate. So the soap should precipitate. Detergent will form suds again, so detergent's really not affected here. And then we're going to test our soap with HCl. So our soap should form less suds. That's a good question. Why should it form less suds? Okay, so I'll let you think about that, but think about it. So if I protonate my carboxylate group, now my carboxylate is no longer ionic. So now it's no longer charged. So it should form less suds because it's not even a good soap anymore because now it's protonated. So when I protonate it, I make it less ionic, so less likely to act as a soap and interact with water and my oil or organic matter as effectively because I've negated the charge. All right, detergent should act as normal. It won't do anything, and that's because remember, pKa of a carboxylic acid is around 5, so it has some equilibrium with its conjugate acid. But sulfate, sulfuric acid, sulfonic acids, they're such strong acids that they don't want to be protonated. So the amount of protonation that occurs will probably be minimal. So it'll probably be less than a fraction, maybe like I can't really say, but it won't be in the acidic form. It'll be still in this deprotonated form in the soap form. So there will be no effect. So detergent should be normal. Okay. Okay, so that's our testing of our soap. Lastly, let's clean up our glassware. So, all right, everyone, what do we wash with? Any ideas? Well, it's a trick question because we're going to use soap because we made it, so we're going to use it anyway. So our product, we would just turn it in our plastic bucket. Sadly, you cannot take it. I wish you could take it. I mean, I don't think it's harmful, but can't let you do that if you were to make it. And then the waste always goes in an appropriate waste container. And then make sure all your glassware is clean. This is a soap lab, so you should probably use your soap to make sure all your glassware is clean. Okay, all right, everyone, that is it. If there are any questions for me, you can stay behind. But other than that, thanks for listening, and I'll see you next week for the last experiment.